everything you learn in algebra leads up to this point of understanding that whatever the degree is, that's how many zeros that you're going to have. And then this book really focuses on writing your answers as linear factors. And this is kind of just, I feel like these two go together. If a function of degree n has n zeros, then it makes sense that if you have a function of degree n, then you're going to have precisely n factors. Some of those are not going to be very pretty factors, and we're going to do some of those today. But if the directions today say write as a linear factorization, that means they want you to write it as factors, not just as zeros. And that's something we kind of talked about yesterday when we were going over that test. Oh, look, and so I kind of wrote it like this. I know you guys aren't a big fan of all these letters, but I can't really put real numbers in there because it could be anything. But if these are the zeros, complex zeros, then you could always write your polynomial as the product of those linear factors. Linear meaning that those are all x to the first power. And remember, zeros and factors kind of go hand in hand. If you know the factors, you can find the zeros. If you know the zeros, you can find the factors. And that's kind of what we're going to focus on today. Ugly, ugly problems. We haven't even officially bought a house yet. It's a long process. Inspection today. Has to pass inspection before we get the loan approved. Then we have to get the loan approved. Well, I've pre-approved, so yeah, it should be. But I have to put all the paperwork. Mary sent it to me, and I signed all of it. That's okay. You read all the fine print? I did not. I mostly just signed all the places that were highlighted for me to sign. I did look it over, but I did not read it. It was like 50 pages. I really didn't read every single bit of it. I trust that my loan officer.
50 pages? How much data you got? Because they might charge you something you don't expect.
No, I read all that stuff. I really know. But then you have to wait. It usually takes like 30 days to close. Like, we're looking probably middle to end of November.
The house built on nuclear, old nuclear.
You don't even know what else I bought.
Yeah, I really do. Isn't it fun?
It's a goofball. They're doing an inspection today, and my husband's like, should we check for radon? Like, radon. Oh, is that something? And I'm like, what's radon? He's like, I don't know, but I think we should check for it.
And watch out.
That's like nuclear radioactive material. I think they would find that in the inspection.
They did. It's in fine print.
No, they haven't done the inspection yet, Logan. The loan has nothing to do with inspection, except for you have to have inspection to get a loan approved. I did most of it.
Got it right. Except for the bad nuclear problems. Nuclear waste problems.
They're so formal. It was built in 2007. There's no nuclear problems.
You're okay with limitations and...
I'm okay with it. It's a good deal. Bargain. When we're talking about dealing with zeros that are imaginary, it's important to remember that imaginary numbers always come in pairs. You're never going to just have one imaginary number. And so just a reminder that if you have an imaginary number and you multiply by its conjugate, the reason they always come in pairs is because when you multiply them out, they're not imaginary anymore. When you multiply an imaginary number times its conjugate, it works out to be a nice real number. So if a plus bi is a 0, then we also know that a minus bi is a 0. So a lot of times they're going to give you problems, and they're going to give you one imaginary 0, and you got to use this to get the other one. because when we multiply it out, it'll work out so nicely. So this leads us to our very first example here. Finally, after all that writing and Logan's nonsense. The papers I just signed, Logan, had nothing to do with like the integrity of the house. It was all just about the loan process and all the money they're going to charge me. Healy. No. Seniors have to go meet with Herb Jones. I'm gonna talk to Mom about that. So we just did a problem like this on our last test. The difference is now I can give you one with an imaginary zero as well. So find a polynomial with the zeros of -2, 3, and 2i. The first thing that you got to remember is this conjugate pairs rule here. So if 2i is a 0, what else do we know has to be a 0? -2i. So that's the first thing that you have to know when you're doing this. Yeah. And then if we've done this a lot last part of chapter 2, if those are the zeros, I could go backwards and I could write my function and say if -2 is a 0, what's the factor? X plus 2. And if 3 is 0, then the factor is x minus 3. And the same thing with the imaginary ones. Don't get thrown off because it's imaginary. You're still just going to do the opposite. So if 2i is a 0, then my factor is x minus 2i. And if -2i is 0, then it's x plus 2i. If you ever work this out and you have an I left in your answer, that means you've done something wrong because we never have a polynomial with an imaginary part in it. It always works out. Yeah, like I definitely recommend let's multiply these two out together. Let's multiply these two out together, and then we could put them together. We don't want to get a big mess with a bunch of i's in there. I feel like maybe we should be pretty good at multiplying binomials by now. I don't even like to write the middle term. I just do it in my head. But x times x is x squared. X times -3 would be -3x. 2 times x would be 2x. So are you okay if I just go ahead and put those together and say I get minus x in the middle? And then the last one, 2 times -3 is -6. And the same thing over here, if I put these two together, conjugates are really great. X times x is x squared. Every time the middle term should cancel out. We could check. X times 2i would be 2ix. X times -2i would be -2ix. So those are just going to equal 0. And then what is -2i times 2i going to equal? Right, remember, and I'll actually write this out since our notes, but -2 times -2 is -4, and I times I is I squared. And what do we know that I squared equals? -1. So -4 times -1, we get x squared plus 4. And if you think about, if you solve that, you would get plus or minus 2i as your answer, because you'd subtract 4, you'd take the square root. But I still got one more step here. If I actually want to multiply this all out and get that polynomial function. So I get x to the 4th plus 4x squared. This times that. And I'm going to take -x times everything over there. So I'm going to get -x times x squared is -x cubed. -x times 4 is -4x. -6 times x squared is -6x squared. -6 times 4 is -24. My x to the 4th minus x to the 3rd. I have 4x squared minus 6x squared. So that would be minus 2x squared. And I don't think I have any more like terms. Minus 4x minus 24. Do you agree with that? Definitely a lot of room for arithmetic errors, so it's really important to to show some work on this, because if you missed the answer, I'm going to go back and see where you messed up. But notice this is a 4th degree polynomial, and we have 4 zeros. 2 were real and 2 were imaginary. But that's not so bad. I like those ones. It takes some time, but they're not that bad. All right. Let's get to some other stuff. Here's another type of problem on your homework today. It says, write the polynomial in standard form and identify the zeros and the x-intercepts. It really is. We're going to do the same type of problems that we did on your test. The ones that said find all the real zeros, only now the directions are going to say find all the zeros. So it's the same type of problem, only maybe a little bit more stuff to do. We'll still use PRZs, otherwise how are you going to know what to guess? You're just going to randomly be guessing numbers. PRZs is a good way to go. Standard form means work it out. So that's kind of what we just did, only they even give us this first step. I wanted to do this because I felt like the directions on the homework would maybe be a little confusing. But standard form just means in multiplied out form. So could you multiply this out? Yeah, those are just conjugates, just like we just did, only now it's 3i instead of 2i. I might not even show much work here. The middle term's going to drop out, right? And what am I going to get at the end? I'm going to get x squared minus 9i squared. I squared is -1. So that would be x squared plus 9. That's what standard form means. It just means worked out. If we factor it back, we'll get back this, right? Right. Because it's plus 9, not minus 9. Right. If it was minus 9, we would just have x minus 3, x plus 3. What do we have? Identify the zeros. Can we identify the zeros from right here? It's already factored out for us, right? What do we do to find the zeros? We just set each one of those equal to 0. And what would the zeros be in this one? Plus or minus 3i. Does everyone agree with me on that? It's just imaginary. Because there are 2 of them, right? This one will be plus 3i. This one will be minus 3i. To solve that from here, you could just set equal to 0, subtract 9, take the square root. But why would we have to do that when it's already factored for us? Zeros, x-intercepts, those mean the same thing, right? But you got to be really careful on that. Zeros mean the solutions to the problem. X-intercepts means I'm specifically talking about where that crosses the x-axis on the graph. So could I say, is it correct to say that my x-intercepts are also plus or minus 3i? Why not? Can you graph this? Can you tell me where 3i and negative 3i are on my x-axis? No. So the reason they say identify the zeros and the x-intercepts is they're trying to point out to you that although zeros and x-intercepts both mean the solutions, the x-intercepts mean actually the real solutions. So in this problem, are there any x-intercepts? No, there's only imaginary solutions, which means if we graph this problem, it would never touch the x-axis, it would never cross the x-axis. So we would say there are no x-intercepts, or there's none. I should say no there, grammatically. You are, but you were just randomly guessing. You don't get any points there.
Randomly guess on the SAT, you get it right, it's right.
But if you randomly guess and you get it wrong, deduct points. Okay, we had the PRZs as ways to help us find zeros. There's another rule that we learned last year, and it's kind of a long rule to write out, but I feel like maybe you're going to remember it as we talk about it. So let's talk about it, and then you can decide if you want to write it all down. But we have this other rule to help us called Descartes' rule of signs. I think I gave him to Mr. McClure. My picture of Descartes. Descartes. Some of my calculus kids think I should name my child Descartes, but I don't think I'm going to go with it. First of all, that's his last name, not his first name. even know if it's a boy or girl yet, so we'll talk about it. I don't know. I don't have anything I want to share with you because you'll just be mean about it.
Why?
Because that's how people are.
I'm open all the
And
time.
I don't even know if it's a boy or girl yet, so I
If
don't.
it's a boy,
I'm not
what do you
serious.
feel like?
Anything below him
Swear?
or Descartes, not Sawyer.
Why?
I eliminate lots of students' names right away because I don't.
Who swears to you?
Not many.
Why?
I feel like I should name it, if it's a boy, I feel like I should name it with ER at the end, which Sawyer would fit under that because I have Parker and I have Gunner as my dog, so I feel like the next one should have an ER at the end also. Symmetry there.
What about?
I don't know. I don't have if it's a female. Okay, so last year we talked about that you could figure out how many positive, negative, and imaginary zeros there are by just looking at how the sign changes. So it's kind of a long rule to write out, but if you have a polynomial of degree n, the number of positive real zeros is either equal to the number of times it changes sign or less than that by some even number. I know you remember doing this, it's just maybe been a while. If I wrote this, like x cubed minus 2x squared plus 4x plus 7, we used to say, how many times does it change sign? And this would be positive, negative, positive, positive. And remember we would count, like, it changes once here, and then it changes back from negative to positive, and then it doesn't change. So how many sign changes were there? 2, or less than that by some even number, and we would say there are 2 or 0 positive real numbers. Any vague memories of that? It's kind of just a very, sometimes a helpful way, sometimes not a helpful way of doing this. So I'm going to show it to you. I'll do it a couple times, but it's kind of up to you if you choose that, use that on your homework. Again, the worst part is writing this rule down because there's not really a short way of doing this. But there's a second part of Descartes' rule of signs, and it says if you want to figure out how many negative real zeros you have, you can also look at how it changes sign, but you got to plug in negative x into the problem. So the number of negative real zeros is equal to the number of variations in sign of f of negative x, or less than that by some even number. So it's kind of like a way to give you an idea of which PRZs to choose. It's also a way that you can verify your answers. Like when you get done, if you have 2 positive and 2 negative, you can check to see, was that an option that I could have? Or could there be all imaginary? That's another option that you look for on this. And then using these 2 ways, we can also find the number of imaginary zeros. So we'll do an example of this, and then we'll see if we like it or we don't like it. We used it a lot last year. Here, let's go to writing. Am I writing this down? Not writing this down. Logan, you writing this down? All right. Just tell me when you're done. Yes. The one downside to this rule, I think, is that these are not guaranteed to be rational zeros. They're just real zeros. So sometimes we get that confused and we think, oh, there's one positive, so I'm only going to look at my positive PRZs. But a positive real zero could be like the square root of 5. And so that's the one thing I would caution you about this. But it is kind of a nice way to get an idea of what to guess first. So let's just do an example here. State how many complex and real zeros the function has. Big day. Just a lot of writing. Big problems. They take up lots of room. It does not say how many possible zeros does it have, so that means we can use Descartes' rule of signs to help us, but that's not the answer to this problem. Is they actually want you to tell me how many exactly complex and how many real zeros does this function have, which means we're probably going to just have to find them, or at least get to a point that we can get down to finding them. First of all, how many total zeros does this function have? 3, because this degree 3, which means I should have 3 total answers. I don't know how many are real, how many are complex. I'm going to use Descartes' rule of signs here just because I want to show you, remind you how to do this. So if I use Descartes' rule of signs to help me, all I'm doing is looking at how many times does it change sign. So I'm going to just write the signs down. This is a positive, this is a negative, this is a positive, this is positive. And I'm just going to count how many times does it change signs. 1, 2. So I could say there are 2, or you keep counting down till you get to 0, positive real zeros. If I was looking for the possible number of negative real zeros, I'm going to do the same thing, only now I'm looking at plugging in negative x. And if you remember, it's not so bad to do this, because when you plug in a negative for an odd number, what always happens? It changes sign. And when you plug in a negative for an even exponent, is it ever going to change? No. And so the easy way to do this is, if it's an odd power, and you plug in a negative, it's going to change sign. So that's going to change to negative. But if it's an even power, and I plug in a negative, nothing's going to change. So it was already negative, it's going to stay negative. If I put a negative in here, that's an odd power, that's going to change to minus x. The constant can't change, there's not even an x in it. So that's where you get those numbers from, by just plugging in positive x or negative x. And you do the rule the same way. You say, how many times did it change? It just changed 1 time. And if I have to count down by an even number, can I go any lower than 1 on that one? But I can't say negative 1. So it's just 1 negative real 0. And we could even figure out how many possible number of complex zeros. You don't have to do this again. I just want to show you. By looking at the possibilities. I know degree 3, there has to be 3 zeros altogether. So look at your options. If there's 2 positive and 1 negative, how many imaginary zeros would there be? Because 2 plus 1 plus 0 has to add up to the total degree, which is 3. Right? But there's also a possibility that there's 0 positive real zeros. So if there's 0 positive and 1 negative, how many imaginary would we have? 2. 0 or 2 imaginary zeros. Again, not required to do that. It's just kind of a little step that sometimes is helpful to you, especially if you have like 37 PRZs. But for this one, my PRZ list is really short, right? What's my PRZs for this problem? Factors of the constant over factors of the leading coefficient. It's just 1, which means I only have 2 numbers to check. Which means, is Descartes' rule of signs really going to help me that much on this one? No, because I really only have 2 numbers to check. And maybe you already did this because you skipped this. But what?
It's like there's still a possibility that's got a positive, negative, or imaginary, so you're still going to check all of them.
You're right.
So why do that?
And hope that it's the negatives that work. The downside to that is just because it says it's negative, does that mean for sure that our negative PRZ is going to work? No, it means it could be negative square root 3, which is why I'm not focusing a lot on this like I did last year, Logan, because you don't have to do this to find the answers. You can still find them. It's a nice way to check your answers to make sure that what you got fits with one of your possibilities that you had. But you're right, it doesn't really work. Because like on this one, I checked negative 1 first because I was like, ooh, 1 negative. I bet it's negative 1. And guess what? Negative 1 doesn't work. Because you get negative 1 minus 3 minus 1 plus 1. So negative didn't work. But if I plug positive 1 in there, 1 minus 3 plus 1 plus 1, I do get 0. So if one works, what could I do now to find the other ones, just like we did on our last test? Yeah, I could divide it out. 1, -3, 1, 1. And the nice thing about when they give you a third-degree polynomial, you only have to find one zero, and when you divide it out, you have a quadratic. And I would be left with x squared minus 2x minus 1. And just so you know, a lot of these today are not going to be factorable because we're dealing with not only all real zeros, but we're dealing with some imaginary zeros as well. So completing the square quadratic formula is definitely something that we're going to want to look at. I'm going to do completing the square on this one, and then my next example, which I think is my last example, I'll do the quadratic formula just to remind you. But this is a great one for completing the square because there's nothing in front that you have to factor out. This is an even number. So if I'm going to complete the square, I'm going to add 1 to the other side. We just did completing the square with quadratic form. So you might be thinking about like just kicking that number to the end. But remember, this is we're actually solving it, so we can actually just move that 1 over.
Why is it positive?
Because I added 1 over to the other side to get rid of that. Right, because I'm not allowed to kick it out when we were writing the equation, but when I'm solving it, I can just move it on over. I'm actually trying to get an answer, like x equals something. And then I'm going to add the same thing to both sides. And what am I going to add there? Half of the middle number squared. So what am I going to put right there? Half of -2 is -1. -1 squared is 1. If I add 1 here, I'm going to add 1 here. 1 plus 1 is 2. And if you factor this, what multiplies to give you 1, that adds to give you -2, x minus 1 squared. I can take the square root of both sides, and I get x minus 1 equals plus or minus the square root of 2. Add that 1 over, and I get 1 plus or minus the square root of 2. There's still a lot of people that make mistakes with the quadratic formula, with their simplifying, breaking the math laws, which is why I like the completing the square if it's not so ugly to do. It's really not that bad most of the time, and people make less mistakes with it, usually. What was my other zero I found? The question asks, how many real and how many complex zeros does this problem have? What would we answer to this one? Is this a complex zero? Right, this is not imaginary. These are all real numbers. So we could say that this has 3 real zeros, which means if we graph that, it would cross the x-axis 3 times. At 2 places, not so pretty, but 3 times. That one only asks how many there are. You might have been able to figure that out without actually doing that much work, and this is where the Descartes rule of signs would be helpful. Let's go back up here for just a second. If I got this to work and it's 1 positive, do you agree that that means there has to be 2 positive? Like if I found 1 positive to work, do you agree that there's not an option of just 1, so that means there has to be 2 positive? And if there has to be 2 positive, what's the only other option that I could put with that to make 3 altogether? Which means, could I have figured out that there were 3 real ones without actually working all the way out? Only using Descartes' rule of signs would I have been able to do that. So, it depends on how you want to do it there, but I just worked it all out. Depends what the direction is. Like, if the direction said this, then you could use Descartes' rule of signs to help you. But if the direction said this, you actually just have to work it out. Find all the zeros and write a linear factorization of the function. My last example. Which we wrote out on the very first page. Linear factorization means we're going to write this out as linear factors when we're done with this. Do we want to use Descartes' rule of signs, or do you want to just skip Descartes' rule of signs? You're not using it? I'm okay with not using it. I use it, but that's just me. We can really do these the same exact way that we did on our last test. The only difference is we're not going to stop if it's imaginary. We're actually going to work it all the way out. which means what's the first thing you should do? Find your PRZs. You have to start by finding some real numbers that work before you can do any dividing out or any solutions like that. So the first thing that I'm going to do is I'm going to list my PRZs. And again, really nice, not huge amount of numbers, factors of the constant over factors of the leading coefficient. No fractions involved here, just factors of 6. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. I have. But I'm just going to start, well, I always start with 1. Because I always have hopes that it works. And if I plug 1 in here, I get 1 plus 1 plus 5 minus 1 minus 6. Does that equal 0? 7 minus 7. Hooray! Which means, what do I do now once I find one that works? Divide it out, see what's left. So I found that one works. Which means I should get a remainder of 0 here. If I don't, then something has gone wrong. I picked this one because this one is a little bit harder because it is a 4th degree to start out with, which means what I'm left with, I just have a 3rd degree right now. Sometimes when you divide it out, your PRZs might change, which means you have less PRZs to choose from. If I did my PRZs for this new function, am I still going to have the same list? I'm still going to have the same list. I do want to point out a little trick that sometimes gets me. Remember that sometimes there's a repeated 0. So for me, it's not an example of this one, but there might be one at some point, or maybe it's algebra 2 I'm thinking of. But like for me, I already checked 1, so the next one that I would check would be -1. But just so you know, if you checked all those other PRZs and none of them worked, 1 could work again. Like it could be a repeated 0, and so it's not a bad idea to sometimes check that same one again. I know I forget to do that a lot. But this is not the example here, because I think -1 works. Did anybody actually plug it in yet? Yeah. I picked a better example. And so then once I find another one that works, I'm going to divide it out again, because now I'll be able to go from x cubed to x squared. I'm going to come up here just so you can see a little bit better. I'm not going to divide it out from the original. I'm going to take my 3rd degree function, so that when I divide it out, I'll get that quadratic, because that's what I want. -1, 1, -1, 6, -6. And I think I have x squared plus x plus 6. Once I get to this point, I have the quadratic formula, or I could complete the square. I'm going to do the quadratic formula on this one just because I haven't done it in a while, just to remind you of it. And lots of you have been using it, so I'm just going to go with it here. Also, don't forget the other answers that we already found. Sometimes it's not a bad idea to remind yourself. Like, we already found that x equals plus or minus 1, so I'm just going to kind of throw that down there so I don't forget to include it later on. Make it up here. Quadratic formula. X equals -b, so that's going to be -1 plus or minus the square root of b squared, which would be 1 minus 4 times a, which is 1, times c, which is 6, all over 2 times a, which happens to be 1. 1 minus 24, do you agree that's -23 underneath that square root? 23, I can't do anything with it, but I can pull that negative out. I can pull that imaginary part out. So I'm going to write that as I radical 23 all over 2. Which means if it just said find the zeros, I think we're done. We found 2 real zeros, 1 and negative 1, and we found 2 imaginary zeros because one's a positive and one's a negative. You follow me on that? Really, again, like Logan said, not anything brand new, it's just throwing in the imaginaries. But it does say write a linear factorization, which means, just like before, if these are the zeros, could you write them as factors? You didn't get this? You didn't get it?
Plus 1/2 squared negative 13.
I got x equals negative 1/2 plus or minus square root of negative 23.
I really think it should be this. But that's totally gonna read. Because we would get x, and then we would get negative 6, and then half of,
Half of 1 would be half. Squared would be 1/4.
so then we would put 1/4 over here. So you would get x plus 1/2 squared equals negative 23 over 4. When you take the square root of that, you have to take the square root of the top and the bottom. So you get x plus 1/2 equals plus or minus I radical 23, but you can take the square root of 4, which is 2. And then when you subtract that over, you really do get the same thing. Right, remember you could break this up as negative 1/2 plus or minus I radical 23 over 2. But you got to remember to take the square root of the top and the bottom, because almost always the bottom is going to be a 4 or 16 or something that you can take the square root of. Linear factors. 1 second here. Let's see if we can get through this. If these are the zeros, could you write these as factors? How would you write those as factors? X minus 1 and x plus 1. That's not so bad when they're nice numbers. But we also want to write our ugly, ugly imaginary zeros as linear factors as well. And it's exactly the same way. You're just going to do x minus whatever your zero is. It's just going to be really ugly. So if I'm going to do x minus this whole thing, you could just put it in parentheses if you want. You could say x minus negative 1 plus or minus I radical 23 all over 2, or the separate one like they did down here. And you could distribute that negative if you want. And then we could do, sorry, I guess I kind of, you really should do this separately. Like, it should be negative 1 plus I radical 23 over 2, and your other one would be x minus negative 1 minus I radical 23 over 2. I should have 1, 2, 3, 4 factors, just like I have 4 zeros. I know I gave you some odd ones on your homework, so check those in the back of the book, and we'll talk about that tomorrow. That's really the new part. I don't have an assignment sheet for you, but make sure you write this down. 3 through 9 multiples of 3, that's only 3, 6, and 9. 17 through 20, 21, 27, and 30. Look at the examples in your book for linear factorization.